Good day, everyone, and welcome to today's DevOps.com webinar. Excited that you're joining us because we're beginning talking about finding zero-day vulnerabilities before the attackers and talking about a Fortune 500 red team case study. It's a great topic, and I'm sure we're going to learn a lot. My name is Mitch Ashley, and I'm going to serve as your host and moderator for today's webinar. So a few housekeeping items that we'd like to take care of before we begin. First, the webinar is being recorded, and the recording and slides will be available following the webinar on devops.com. Participants will receive an email with the links to the content. We definitely encourage questions. There'll be time at the end of the presentation for questions for our speakers. They love questions. So we invite you to enter your questions into the GoToWebinar control panel, the questions section. Last but not least, we're awarding 3 $50 Amazon gift cards at the conclusion of the webinar. So please hang in there and find out who wins. So now let's get right to our topic. Finding 0 days before the attackers, a Fortune 500 red team case study. It's my pleasure to introduce two speakers today. First, Chetan Kaneki, who is CTO and co-founder at Shift Left. And we have also Shannon Leitz, who's director of red team at Intuit. By the way, Shannon is the inventor of the term DevSecOps, so we've got kind of royalty here today. So happy to have both of them on hand. We're going to start with Chetan. If you'd like to go ahead and take it away, thank you.
Absolutely, thank you. Appreciate the introduction and welcome, Shannon. It is an absolute pleasure to co-present with you today. So
looking forward to it.
Absolutely, thank you, Shannon. The topic for today is finding zero-day vulnerabilities before attackers. And it's a very interesting topic, so let's dive straight in. I want to start this presentation with describing what the underlying structure of discovering vulnerabilities is. As we all know and have interacted with various applications, most of the applications that we use today is powered by graphs, because graphs are a powerful and versatile data structure that easily allows us to represent relationships between different types of data. So let us use a few examples to drive and understand why graphs are so powerful. Long gone are the days where intrepid travelers got lost in back streets, fumbling through map books as they paused to ask locals for directions. Unquestionably, the digital map has revolutionized the ease at which we can travel, whether by car, plane, train, or foot. Punch your destination in your Google Maps search bar, and you'll see directions, alternative routes, and real-time information appended to your route as well. Switching context, digital maps displayed on our browsers, cars, and mobile devices are powered by applications that are built, packaged, and deployed in data centers to serve our customers. These applications begin the journey as source code, where we as engineers initialize and create a project, name it, and effectively author function bodies encompassing a set of variables, communicating with other functions belonging to either the same package or different packages, which together is composed, compiled, and deployed into a microservice mesh in order to serve our business needs. Coincidentally, when engineers reason about code, they are also thinking in terms of connected graphs, meaning how a set of connected functions communicate with each other to serve a certain business need. When code is compiled and deployed in production as microservices in a dense communication mesh, AppSec and operations team begin to derive their insights with a topological view like this. And again, these views almost look like connected graphs. From an attacker perspective, the vulnerability discovery process can be likened to solving puzzles like mazes, jigsaws, or logic grids. One way to think about it abstractly is to see the process as a special kind of maze where you don't immediately have a bird's-eye view of what it looks like. And as the attack sequences are applied on the application, a map is gradually formed over the time through exploration. And the final map is almost never clear, but sufficient to figure out how to get from point A to point B. So let us pause and reflect as to why graphs seem to be the common construct of reasoning across these use cases that we spoke of, by attempting to answer the following questions. Why are graphs interesting? How can we represent code as graphs? And when we do, what can we learn from it? Graph theory boils down to two fundamental things, that is, places to go and ways to get there. So often a graph refers to a collection of nodes and a collection of edges that connect pairs of nodes. Nodes can be places to be and edges ways to get there. So as you see on the slide, by an illustrative example, an organization is represented as graphs, where we have entities like employee, department manager, department, all connected together with metadata appropriately tagged upon it. Coincidentally, the code that we write powering all these applications need to be compiled and packaged before they're deployed into production to serve our customers. Compilers that actually compile our code also use graphs to reason about code, and using this knowledge, it effectively optimizes our code from a performance perspective. To start with, we write programs in text, and these programs have to be verified against a certain grammar adhering to the programming language that we're using. If we do not adhere to the grammar, it fails compilation. The next step is, after adherence to the grammar, the compiler begins to assess control flow within the application, which effectively represents the order of statements from an execution perspective. Again, this is used to optimize the code further. Lastly, there is data that is either created, transformed, or initialized as our programs run. So there is a data flow graph that is also comes alive within an application, which tells us how variables are initialized, transformed, and exchanged or dispatched between functions. So we at Shift Left invented a technique that takes these three seminal representations and combines it into one unified, powerful construct called as code property graph. This came out of research by our chief scientist, Dr. Fabian Yamaguchi, who defended his PhD thesis, which was titled Code Property Graph, by creating a formal data structure and assessing a very large code corpus, which is the Linux mainline kernel. Upon assessing the Linux mainline kernel, he was able to identify 88 vulnerabilities, out of which 18 were previously unknown. So what is the code property graph? If we examine it from a workflow perspective, the code property graph receives as input either source code or bytecode written in any programming language, and thereafter converts it to this joint data structure. And after converting it to this very joint and powerful data structure, there is another step, or what is called as semantic tagging, that is applied on the graph. The purpose of semantic tagging is to effectively mark areas at which our consumers are interacting with the application, which is essentially called as sources, the areas where our application is communicating outbound with resources like database, memory, file system, and other microservices of the socket, which is called as sinks. And in between, as data is created, initialized, or updated, these appropriate data containers are tagged as data elements. Now, as workflows are triggered, there are various transforms that are happening. And appropriately, these transforms are tagged as transform functions too. The consequence of first creating the graph, applying semantic tagging over the graph, is to provide the purpose to ask intelligent questions from a security purpose over the graph. And here is a simplified representation on this slide that effectively enables us to model whether a certain weakness exists in the code that would enable an attacker to exploit that particular path. Again, this is an oversimplified representation. To illustrate a typical SQL injection susceptible flow, we have a source which accepts input from consumers on the HTTP channel. And through the path of the workflow, this particular flow communicates with the database as a SQL statement is framed and executed to either look up value from the database or write values to the database. Now, if we do not have transform functions from the point of source to the execution of the query, most likely that path carries all symptoms that could trigger SQL injection. Having semantic tags over the graph enables us to create more complex models, and using these models, we can automate the ability to extract and ask questions of whether your code base carries vulnerabilities. With this, I'd like to shift to Shannon, who's going to describe how this particular graphing technique is used in our organization practically. Over to you, Shannon.
Hi there. It's great to be here today. I currently work in an organization where I run a pretty large red team, and with 4,000 developers, we specialize in financial products, both small business and tax. Having the ability to get ahead of and stay ahead of adversaries is something that is quite challenging. And understanding this graphing technique became instrumental to us. And I'll just explain a little bit about the journey to give a sense of why this is such a huge improvement on trying to find exploitable vulnerabilities. Next slide, please. So along the way, and I'm pretty much a fan of Simon Wardley's work, this is a Wardley map. And, we were, when I first arrived at Intuit, looking at trying to evolve with the cloud and starting to look at this work. And so mapping out commodity space and really understanding next generation capabilities gave us a lens for what it was really going to take and how much of a leap some of these things were going to be, and really where the maturity level of capabilities was when we started this process. And so I did this map quite a while back, and it probably needs to be updated to be completely transparent. But at the time, you can see one of the things that was really big for us was the cloud was starting to cause a lot of shifts. Things like agile weren't necessarily, pulling on the cloud becoming a thing, but basically compute wasn't keeping up. And so developers really needed something different. And that has really changed a lot of what the security industry has been going through, because transformation and development has really led to some of these things becoming a bigger challenge. So I think it's really important to realize that that's caused major shifts, lots of emerging capabilities in security, and these new emerging capabilities have a lot to do with that transformation. Next slide, please. So with that said, in 2012, it was go to the cloud. But at the same time, there was a lot to be desired from a security perspective. At the time, the cloud providers really didn't have a lot of security capabilities. There wasn't major levels of encryption or key management. There wasn't logging built in. You didn't have things like audit trails. You also didn't have a lot of the features that were out there. You basically had compute, storage, and essentially what was equivalent to like a host-based firewall. And that caused its own challenges. But I think one of the other things that really happened is as the cloud providers have added more security features, speed's been picking up. And so security folks are challenged, more with trying to figure out, how am I going to evolve, or am I going to become extinct? And that's really led to some interesting conundrums, right? So if you want to move to the cloud, what does security really look like in the future? And that's why DevSecOps became a thing for us, starting back in 2012, trying to figure out what's it going to mean to either embed security in with a developer or try to transform. And next slide, please. So evolving from extinction, shifting left. What was interesting was I think I wrote a paper on shifting left, gave a couple of talks on it, and next thing you know, there's a company called Shift Left. And I thought that was really interesting because, at the time, just even mentioning shifting left, talking about what it meant to chase trust upstream, talking about the design challenges of security for developers, for people creating software. Mark Andreessen said software was eating the world. Well, in 2019, it feels like it ate the world, especially when toasters have software, and your washing machine could take over your refrigerator. Lots of those things cause lots of challenges. IoT has become, interesting segments for taking over a network. There's lots to be thought about, and it's becoming more and more complex. We're starting to see things like software-defined networks. Back when I first got into computing, that was the nirvana. I remember when it was called utility computing and it wasn't called the cloud yet. And so shifting left for me has sort of been in my blood from the early 2000s. And I think that's what led to some of the innovation that I've been leading, is that, it really needed to become something that was a change. Next slide. So, with Red Team, I think along the way, it was somewhere in the 2014 timeframe, it was pretty clear we were trying to get the cloud to have more security features. And all of a sudden we were like, well, now that the cloud has security features, how do we improve on security? How do we go faster? What does that look like? And along the way, we tried everything. Do we embed security folks into teams? That was sort of a bust, because apparently security practitioners actually specialize, which means that no two security professionals are sort of alike, and trying to embed them into development teams can be very challenging. So, one of the things that we came up with in my team was to start thinking like adversaries. If we were thinking like adversaries, we could provide more guidance, more understanding of what it meant to build more resilient software. And that's when I met up with sort of the rugged DevOps troop and started bringing more of this DevSecOps to life, and took probably one of the most radical left turns, which was red teaming things from inception all the way through. What did it mean to, folks were touting threat models at the time, and I had threat modeled before. I even taught threat modeling. And instead, we looked at things like attack maps. We knew developers were making choices, and we could help them if we could understand their choices earlier. The concept of red teaming has got a wide variety of capabilities, a wide variety of approaches. Tools are not very mature. There's lots of sort of what we call hocus pocus. You're constantly commenting about crown jewels and looking for some of these things. But trying to do these things in a company that's effectively trying to build software to help solve problems for its customers, trying to stay ahead of adversaries is also a cultural impact. And trying to help people means waking them up, getting them to be more aware to these problems, having them really understand. And by the way, a lot of these problems are very complicated. Trying to find an exploitable weakness in software is no easy feat. So, we said, all right, well, we're going to do this. We're going to take on the challenge. It's really hard to do. So what does that really mean? Hey, let's look at the tools that are out there. Maybe we can get jump started, right? And so the next thing that we did, if you go to the next slide, is we said, all right, we're going to look at the traditional practices. We're going to manually test, and we're going to research. We're just going to pour all of our time into finding the most important things. And then we realized the barrier to entry is much easier. You open up a computer, you look at some software, you start doing code reviews, and then you realize, wow, this is really hard and time consuming. I can't figure out how this thing links back to that thing. And there's a lot of dependency on tester skills, and growing tester skills when it comes to the industry. If you look at the security industry, it's been significantly undersourced for a long time. It becomes rare discoveries, right? You see very few actual discoveries. They come every few months if a tester's good. So on average, you might see a good tester have, maybe a dozen of these a year, and somebody who's just working on it might get one or two every couple of years. And so, that becomes really challenging if you're trying to get ahead of adversaries who are also looking at these same things and figuring out what's most important to them. There's lots of techniques at their disposal. And oh, by the way, we have to be right 100% of the time when you're defending. And an adversary really only has to be right once in a while to really take a lot out of an environment. So if you go to the next slide, the next thought was, okay, well, manual is not working. Let's work with these static code analysis tools. Let's try to find stuff. And all of a sudden, false positives were just brewing. We're like, well, what do we do with this thing? Can we use it to exploit? We found tons of stuff, but nothing was really leading to full exploits. We weren't getting to that end goal, which was, how are we going to make our software more resilient by blocking out exploitable surface if we really can't weaponize against these things, figure out if they're actually important, figure out how long these activities are taking place. And it took a lot of infrastructure to maintain these tools. There's been a really poor experience between sharing them between security and development. Security folks would go work with the tools, get a bunch of reports on vulnerabilities and weaknesses, and hand those over as large CSV files that still needed to be reviewed. And so not the most elegant solution, if you ask me. So that caused the next part of this journey, which is, we're going to red team. So we're really going to focus on exploitability. We started to evolve. And one of my beliefs is that if you measure something and you put out that goal of measuring something, you can do well at it. And so the idea was to develop this metric, securability, and really at first it was just an exploitability metric. Can we find exploitable surface? And imagine telling somebody that they've got a 0.0001 problem. And they're like, well, that's great. Is that a big deal or a little deal, right? And so we realized that we were speaking about these things in weird ways. And so we evolved this metric to really be the 5 nines of security, trying to make it so that you understood whether you have a resilient application or not. And we will be continually working through this. I think it's one of those journeys that will continually mature over time, but it also is a guiding light for tools in the industry that if they're not talking about the 5 nines of security, if they're not adapting to measuring some of the surface area of an application, and they're not helping a developer to understand their 5 nines, that becomes a big deal. And next slide. So we kind of look at exploitability in these 3 levels. There's the implementation weaknesses, which you enumerate. So you use tools like Nmap and some of the scanners that are out there like Nessus and Qualys and Nexpose and a variety of others. If I've left any out, I can tell you there's a laundry list of them, and we've gotten good at many of them. Protocol analysis, really looking at when you build an application, business logic. And so if you look at trying to evolve your protocol analysis understanding of something to understand its weaknesses, there's very few tools in this place. That a lot of the things that you discover through protocol analysis are reverse engineering tools. You might leverage techniques like attack trees. And then finally, the other part of exploitability, as we all know, is code, really trying to look for the anomalies in code, not just the weaknesses from implementation or protocols that are being placed on top of them, but the actual code that causes the information to be passed from one place to another. And so where we're focused here, if you go to the next slide, please, is with the tools that are helping with graphing techniques is to essentially work on the code and the code analysis sector of this space. And so what we did and our strategy was, let's go looking for attack capabilities and attack trees. And like I had mentioned, I saw the Shift Left name a long time ago, and it just didn't register to me. I spoke at a conference with one of the founders of Shift Left, and he talked about attack graphing. And funny enough, that's actually what led us to Jorn. And this capability is an open source project, really cool, actually pretty complicated, but we found out that we could have some of our interns work with it, and they could find things. And so early on in our journey, we found out that we could actually find exploitable weaknesses using this methodology. And that's when we realized we need to really double down on it. And we started pursuing it more effectively. And ultimately, that led us to Ocular, which is built on a lot of this capability that was set up through attack graphing. And Fabian, who started this project, is just amazing. He's got a lot of insights around attack graphing. We are now capable of using these products, and our team is pretty aggressively using them. If you go to the next slide, that strategy is really led us to results that have become really interesting. As an example, we've published 3 times more CVEs. The team is becoming better at leveraging attack graphing. As far as trying to make these things happen, we've been able to perform automated scans of our third-party dependencies and find 0 days faster, stuff that we're able to weaponize, exploit, turn over to third parties and open source projects, make sure that they're getting patched more effectively, and aggressively reducing the attack surface through these methods so that it doesn't become a surprise, what's actually happening in the industry from the standpoint of research. Next slide, please. So what's up for the future? I will tell you, if you saw what I said earlier about implementation and protocol analysis and some of these things, we continue to want to advance our graphing upstream. Graphing can be a really interesting technique for things like design analysis, for protocol analysis, trying to find exploitable opportunities, advancing our understanding and our precision in exploitable opportunities, really creating more test catalog. And then ultimately evolving our automation and our intelligence capabilities so that, eventually when we're seeing research, it could help construct some of these capabilities. And so Ocular has become a big part of that toolbox for us. Back to you. Let's take a look at the demo.
Absolutely. Thank you, Shannon. Thank you for that very insightful and practical overview of red teaming. And by the way, the name Shift Left, when we incorporated, we were inspired by a certain post that Shannon had created. And this seminal post of hers speaks of Shift Left on her devsecops.org blog. This actually inspired all of us to actually take this literally and build a company around it. But kudos to you on that, Shannon, before I proceed to the next slide.
Thanks.
In this section, we're going to speak about Ocular, and what I'm going to do is demonstrate some of what Shannon spoke of about Ocular and its capability of traversing attack graphs. And why is this? We also touched on why graphs are relevant, and so we'll see graphs come to be as we interact with Ocular. Very quickly, Ocular is a software distribution. It's very similar in vein to Spark or Jupyter, if you use these platforms from a data science perspective, where you install the platform and this platform sits in your secure enclave, and you begin to interact with that platform to serve your needs, meaning you conduct inquiries on this graph, which is yielded out from your source code, to ask interesting questions about weaknesses and vulnerabilities. As next steps, you can take those questions, convert it to scripts, as you will see shortly, and execute it in an automated fashion in your CI/CD process. So very quickly, I'm going to shift to a demo mode. So briefly, I will unshare and reshare again. So like I mentioned, you can install Ocular on a pre-configured machine with the appropriate resources. And after installing it, you can fire up Ocular in inquiry mode to ask interesting questions pertaining to your application's graph. And like we stated, Ocular works with source code and bytecode written in any programming language. And we are progressively adopting or onboarding several programming languages in the roadmap. For this demonstration, I will use Java as an example. So as we create and write code in Java, the outcome is either a jar file or a war file, which is nothing but a compressed archive of bytecode that we effectively package and deploy in production to serve our customers' needs. So the first step in Ocular is to create the graph. So there is a very succinct API, which is create CPG and SP, which accepts as input a jar file or war file. So as we fire up the prompt and issue this command, create CPG and SP, a graph is created in our workspace and loaded so that we can begin to interact with the graph and ask interesting questions pertaining to security. Similar to Jupyter and Spark, Ocular has this concept of workspaces. You can load one or more graphs, and all these graphs are created and cached into this workspace so that you can interactively switch contexts between graphs of variant applications that you've loaded in Ocular. The next step after creating the graph is to load the CPG, because as we've established a session with Ocular, we would want to load one or more graphs within the scope of the session and begin to interact with it. So this command load CPG enables us to load the graph and begin to ask questions. So I'm going to ask a series of questions pertaining to how the code looks like. So let's start with some simple questions. The simple question is, give me all sources in the code. Like we stated earlier in the presentation, as we write web applications, daemons, or crons, all of these have certain characteristics to it, where the application bootstraps and is either listening on the socket or accepts certain environment variables and goes through the startup process. So as the graph is created, like we spoke of earlier, all sources are automatically and semantically tagged. So by virtue of it being tagged, we can simply ask by a simple command, give me all sources in the application. So again, the command is cpg.source. For all methods, give me the full name. And note that upon executing, we've got a laundry list of methods with their appropriate arguments represented as sources in your application. And note that the source could be an interaction with the file system, listen on the socket, or a certain decode function or an encode function. Likewise, we can inquire to identify all sinks in the application, meaning all endpoints that the application has where it is interacting with external resources like file system, database, socket, where it's communicating with other microservices, etc. Again, the command is simple, where we're literally replacing source with sink, where we say cpg.sink, and you would have noticed an l.map. Given that Ocular is foundationally based on Scala, you get the benefit of using Lambda expressions and data structures that are available in Scala. So now you get a list of all sinks or outbound interaction points in the application. Now, this is fairly interesting to take a gander at, because in certain cases, you might want to have a constraint set in your company that no application should ever execute runtime.getRuntime. And if that's a constraint set, you can literally take this foundational API, apply a bounds checking to see if someone is using that API, and then fail a build once you interacted or applied in CI automation mode. Now, as we write applications, our applications are creating literals, where if we are creating strings and messages that we send forth to the browser where our consumers begin to see them. So there's a simple command which is cpg.method.literal.code. This command provides all hard-coded literals in your application. Now you may ask, why is this important? It is interesting and important because in certain cases, engineers might inadvertently hard code an AWS credential or an Azure credential in your code. And perhaps if they check that code in the open source, it would lead to a leak, which would further compromise your credentials, leading to an ATO. So this particular foundational API can let you query for those constructs and identify if any keys are leaking, which you will shortly see as a double click into data leaks. Likewise, there is another very simple API, which is CPG.type declaration. And type declaration gives you a laundry list of all types, albeit system type or user types, defined in your code base. Again, inquiring for types is a basic foundational construct for certain recipes that I'll talk further, because it gives you cues of whether someone is using a certain type, either in a malicious perspective or by mistake. And we will shortly see as we delve into business logic and data leaks of how these foundational APIs come into life. Again, we can also inquire all methods, albeit sources or sinks defined in your code base. For this, we call for cpg.method. We get the full name bound to the associated parameter with the eval type, meaning if you define a primitive type like string, integer, or a user-defined type like class user, class product, that type can be extracted associated with the name of the type. So again, you can choose to represent this in any which way you want, but foundationally, given it's based on Scala, you get a list representation of the results. And here again, it's very simple, where you get the method name and the type associated with the name of the type. Now, given that we took a quick look at the foundational constructs, let us go one step further to see if Ocular can provide us with a very succinct and simple API of all vulnerabilities discovered in the application. Again, a very, very simple API, which is finding, where you literally say cpg.finding, and you get an entire list of all flows in your application bound to a specific vulnerability. Now, this is almost akin to you asking a simple question and getting an OWASP categorized list of vulnerabilities that exist in your application. You can take this information and use it to drive decisioning in your CI pipeline. We score results, and you can use that score to identify whether you want to fail a build or pass a build, depending on the severity. And this severity is inherited from the OWASP Foundation, given that majority of the security operations folks are acquainted with the OWASP categorization. Again, there is a very succinct API, which we call as get attack surface, because we've heard how to effectively do red teaming, as Shannon spoke of it. During the red team process, there's typically the first step called as enumeration or discovery, where red teamers use a specific set of tools to discover exposed endpoints across a plethora of applications hosted. And often exploration takes hours to days, but with Ocular, there's a simple command called as get attack surface. Upon executing this command, you get the route, you get the associated source function mapped to the route, and all sinks, one or more, mapped if a particular interaction is initiated on the route. Now, this is really interesting data point that can be literally exported into your Burp Suite or your Zap to conduct targeted attacks. Because often you have little or no understanding of the attack surface, which means that you have to spray and pray attacks across each route. But with this, you definitively understand that this route 1 is communicating with the SQL database, and most likely you can target and specifically attack SQL injection type patterns on this particular route. So these are the foundational constructs of Ocular that I just spoke of. But now let us switch into specific use cases, and we will look at the use case and apply those interactions on the Ocular prompt. We touched on the concept of data leaks. We often hear of data leaks literally on a weekly basis. But what I'd like to do is drive this case file discussion with most recent data leak that happened with Twitter, where Twitter advised its 330 million users to change their passwords after a bug was exposed, where passwords were leaked in plain text to the log file. And then the RSS log daemon aggregated these log files and dispatched them to a dashboard like Splunk or Sumo Logic. Now, the side effect of this is that administrators were able to see consumer passwords in clear text. Now, this case file was detected when Twitter was going through its GDPR compliance audit. It's not just Twitter, but all of us are a victim to the situation, because engineers often want to log as much as they want so that they have clarity during triage process. And as a consequence, sometimes critical data is leaked. Now let us look at what data means. We spoke of user-defined data, system primitive data, etc. So data has, as we know, data originates in code, and there are microcontainers. They're small representation of what is held from either a consumer perspective or maybe from a system resource perspective. So let us look at a few examples. The first example is a user-defined type, where we define our data structure called as user, either by using struct or class, depending on the programming language we're using. And all of these have properties bound to it. Note that from a PII, SOC 1, SOC 2, GDPR, these elements have criticalities and confidentiality scores associated with it. It is important that when we initialize such data elements, we have to treat these data elements with care. We also spoke of hard-coded credentials. Most likely as engineers, we hard-code credentials when we're dealing with provisioning our workloads in public clouds or private clouds. And if certain things like this are detected, the next affirmative action is to use a vault and recall that information from the vault and assign it to a variable. So if data existed in these forms, how can we assess its existence and thereafter identify how data is transformed and exchanging hands or passing through functions in your application and eventually exiting the crevice of your application to either a log file, a network, or a file system? Ocular provides very succinct API, which I'll demonstrate shortly, for you to first of all identify all sensitive data elements in your code. And in order to achieve this, we have built a natural language processing technique to identify how things are named or data elements are named in your code. And thereafter, we begin to follow those data elements to see how they're participating in workflows. Again, using a very simple API where I'm saying give sensitive user-defined data types, restricted to a certain package, because often our code is comprised of various namespaces and packages. So by executing this API, I got a list of data structures that have been classified as sensitive. And in this case, given that this application has a model of type order, user, and email service, it is classified as sensitive because it happens to be encompassing properties like social security number, first name, last name, address, etc. Now, given that we have that information, let's go one step further and ask if any of such information is leaking on a log channel. For that, there's a very succinct API which says, is PII leaking to logs? Upon executing this function, you get a set of flows. And Ocular has a pretty printed representation of traces and flows. As engineers, all of us are acquainted with exceptions because it gives us a lot of information. Likewise, a trace stack essentially encompasses the data element, the line number in your code at which it is initialized, the method encompassing that data element, and the file encompassing the method. Now, this flow is sequential. It's literally a graphical traversal of point of origin to destination. And here we clearly see that order ID is being initialized, going through a series of transforms, and siphoned to a log channel. And it is clear here that it is leaking because there is no encryption, obfuscation, or redaction happening in path. Likewise, we can also quickly inquire to see whether any such PII data is leaking on an email channel. And you will understand why this is important shortly when I walk through another use case from a business logic flaw perspective. But here clearly that we have an order with an element of type email address, which is again going through a series of transforms and eventually being attached to a MIME body part and then sent over the email transport channel. So clearly, again, we have a critical piece of data being emailed in clear text without encryption or redaction. Likewise, we can quickly inquire and conduct various degrees of checks to see if data tokens are leaking on channel. Like we stated, we sometimes mistakenly log AWS keys and credentials, and here's an evidence of a AWS access key ID, which is initialized or hard-coded in servlet target file that is being dispatched on a log channel without redaction and obfuscation. A fundamental mistake that all of us have committed in the past or are committing as we progressively speak. Likewise, we spoke of environment properties, because if we identify hard code, the next affirmative step is move that to the environment variable or a vault. But eventually, again, that's looked up and assigned to a variable, which could be a primitive type of string. And now that variable could again be passed to the log, meaning the mistakes continue despite of us fundamentally moving a hard-coded element to an environment property. Again, we see that as a trace, and using that trace, we can identify that a leak is imminent, and we can take affirmative action by failing the build, because these are preemptive steps that we can take to ensure that we always stay compliant and we never leak our customer-sensitive data. Switching context, I like to speak of another use case called as business logic flaws. You know, this is a fairly pervasive category that is getting a lot of attention these days. But let me describe what business logic flaws are. A business logic flaw is defined as a security weakness or a bug in the functional design aspect of the application. Note that it's not a vulnerability, it's not a code-based flaw, but a logic-based flaw. Because as proper stewards of application design, the first step that we do is architect our application and then implement our application, measuring to that architecture. And sometimes if we have a flow that is weak, an attacker can bypass a step and effectively take control of your application with malicious intent. We see this play out over and over again, but what I'd like to do is illustrate this with a case file. Not too long ago, First American Financial Corp leaked hundreds and millions of title insurance records via a simple mistake, which I'll quickly illustrate. This particular category in the world of OWASP is called as IDOR, which is Insecure Direct Object Reference. We saw this again play out with Jared and Kay Jewelers, but if we have to deconstruct this, there were two events that were happening. When a consumer fulfills a transaction with that particular vendor, the next affirmative action is to send an acknowledgement over email. So what was happening with these vendors was that the primary key ID of the database was appended to a URL, and that URL embedded in an email and sent to the consumer as an acknowledgement of the fulfilled transaction. So when the consumer clicks the link, he's directed to a page that gives him his or her order status. But what was also a mistake that existed in this flow was that this ID was predictable, meaning the consumer could keep guessing forwards and backwards and look at other customers' information. The second issue was the link directly displayed the information without authentication, which led to the cross-tenancy access. Note that there are two conditions that exist separately, but in unison caused for this business logic flaw to manifest. Very quickly, to demo for these conditions, again, Ocular provides a very succinct API using some of the package scripts the first API that I'm going to call on is to ask if there is any critical information from the database, like a primary key, leaking on to an email channel. And for this is IDOR to email. IDOR stands for Insecure Direct Object Reference. Lo and behold, you get a tracking trace, and the trace essentially is explaining that we have an email order ID that is participating in an email append leading to that critical information being sent on a MIME body of an email directly to the consumer. So this is the first symptom that exists that tells us clearly that we have predictable sequence leaking. The next condition to check for is if we have any authorization applied on that path to ensure that every route is redirecting the user to first authenticate before they see their detail. Again, this provides a greater amount of detail to let us know that they are a certain set of routes that are doing conditional checks, like is user enrolled. But if I quickly flip the flag to false, I get the negative list, meaning here are a set of routes that are actually not authenticating, that would lead for an IDOR, or Insecure Direct Object Reference, to trigger. With this and a variety of other recipes, we can identify very detailed business logic flaws that could effectively negatively impact your application. Let us quickly look at a third category called as rootkits. This is a fairly new category, very pervasive, because in large organizations you have various parts of your software development outsourced to certain other companies. And as your organizations go through the upheaval of profits and losses, most likely you'd have employees losing their jobs as a consequence. So one employee with malicious intent could sabotage your applications by inserting a certain malicious code snippet that could effectively escape basic code review. And by placing this rootkit, either at a certain scheduled interval, this rootkit could be triggered to implode within your application, causing some degree of catastrophe, or triggered by an external action. Again, examining case files, this has played out and continues to play out. We saw this happen recently, at an organization where an IT guy annihilated 23 of the ex-employees' AWS servers by laterally moving from the application to the host. So let us examine one such example.
If I could jump in here, we're running short on time. Are you okay if we jump to some questions? Because we've got a number of them from the audience.
This is the last, so I'll be consuming 1 minute, and absolutely, this is the last use case, and after which we'll be jumping quickly.
Okay, thank you. This is step on your presentation.
Absolutely. No worries. This is a real use case called as fork bomb. There are a variety of fork bombs being implemented in different programming languages. And this was a real case where an employee planted a fork bomb in the code that was triggered at a certain interval that caused the compute resources to be in kernel panic, meaning it continuously went into a mode where the system crashed. And it was fairly hard to detect. And I will quickly illustrate how Ocular can be used to detect this. We have a rootkit package that is available. And using rootkits, using the CPG, we can effectively query to identify if such patterns exist in the code. So there is a succinct API that's called as get suspicious literals, where we identify if an engineer has hidden a code snippet in plain sight, which could be an base64 encoded string, where we infer and extract what it means, which is essentially a Java class. And we also interpret it as Java code, and then further trace to see if this particular obfuscated element is being passed to a compiler to trigger a rootkit. So these are various use cases that we have, and several more. All these use cases can be taken and composed as scripts and executed in your CI pipeline to continuously identify for business logic flaws, backdoors, or unknown vulnerabilities that exist in your code. With this, I'll complete the presentation and take questions. Thank you very much.
Great. Chayton and Shannon, thank you so much for the presentations. Let's take questions from our audience. The first one is for you, Chayton. Is it possible to run Ocular queries as automated regression tests?
Absolutely, yes. So
Great.
Ocular, what I just demonstrated is Ocular running in inquiry mode. But what you can do is take your inquiries, export it to a script, and run that script continuously in your regression suite or in your CI/CD pipeline.
Fantastic. Next question is for Shannon. Do you think having access to source code undermines the value of black box testing?
Absolutely not. I think one of the issues is if you're going to get ahead and stay ahead of adversaries, having an insider capability means that you have information at your disposal that helps define these things. I think the notion of red teaming, black boxing is really about understanding from a inexperience level and trying to compete at the same speed as an adversary. So I just think we really need to change how we think about that in the red team concept and also in the industry, because there's a lot of advantage to being able to look at something, understand it, and really get into the nuts and bolts.
Thank you so much, Shannon. Next question is back to you, Chayton. When will Ocular be able to test Node.js-based code? A kind of related question is what languages or types of projects are supported by Ocular for analysis?
Absolutely. At the moment, we support C, C++, Java, and C# in the .NET family. And on our roadmap, very soon, the first language that would be released is JavaScript and Node.js. Following, we will be releasing Python, Golang, and few other languages like Scala over the JVM, Java Virtual Runtime Framework.
Excellent, thank you. Shannon, we've got another one for you. You mentioned that interns helped you with the graphs initially. Where can one with little or no experience with graph analysis and security start from? And is there some source that can teach you to read and analyze or see weaknesses and anomalies within graphs?
It's a great question. I think that when we got involved with Joran, that's when we started to evolve these capabilities. Are there open information about this? Some of the information comes from attack trees. There are numerous papers on doing these techniques. If you were to look up Fabian Yamaguchi, you're going to find a lot of the information that's already out there. Do I think there's an opportunity to provide much easier ways to learn it? Yes, but I also know that the barrier to entry for an intern has actually been pretty low. So I think some of these tools that are evolving are really helping with that.
Excellent, excellent. Let's go back to you, Chayton. Files in Ocular remain local. In other words, it's the source code that's uploaded anywhere?
Everything is local, meaning Ocular is a software distribution that you install on a box in your secure enclave, either on your physical host in the data center or in the cloud. So none of the code leaves your premises, meaning that as you compile your code, you import the compiled unit of that code into your Ocular session installed on your local box. So there's no code that leaves your premises outside the realm or to any other cloud.
Excellent. I'm sure that's a good answer that they'll appreciate. Shannon, back to you. In Shift Left, we're talking about enabling developers to perform AppSec. Is this a reliable method as opposed to experts doing AppSec?
Yeah, I think that this is an opportunity for developers to take a tool like this and really look through their code. I think having a separate capability with AppSec is absolutely an opportunity as well. Is there one versus the other? No, I think it's actually what works best for the company and the people that they get in terms of skill set is really the way to drive for this. And I believe that making tools open and available to everyone that's developing software really does help to make the software more resilient. So I don't think it's actually a silo that's needed. I think it's important to weave these skills.
Appreciate your thoughts on that very much. Chayton, is there an API to integrate Ocular with an existing platform?
Absolutely. Ocular is based on the Scala platform foundationally, which means that you can write any inbound or outbound API interaction. we have created recipes to interact with GitHub, Jira, and other systems like Nexus IQ Server, etc. So exporting results from Ocular or importing insights from other systems into Ocular is fairly trivial.
Excellent, thank you. Let's go back to you, Shannon. Won't the remediation process be more efficient when we take the inputs from various security tools using a vulnerability management platform and then provide a single pane of glass view that helps prioritize the vulnerabilities?
I think it is really important to look at your vulnerabilities, determine your weaknesses, have a pane of glass. I think having a exploitability measure does help with that. Having that securability pane of glass and feeding everything into it is important. I think a tool like this, a capability like attack graphing, can help to further refine and create the complexity understanding in these tools. I think just simply scanning something from an outside perspective isn't enough. I think we have to get into moving over to both design and the code to be able to understand what's really happening.
Great, great. All right, we'll give our last question to Chetan. Given that Ocular analyzes bytecode as opposed to source code, is it still valuable for analyzing programs that have been compiled without debugging information?
Ocular can work with source code and bytecode, and that particular choice is applied based on the programming language. And debug symbols are not necessary, even if you're dealing with bytecode compilation, because we take into account the binary signatures in the source code and its applicability from a traversal and flow perspective.
Actually, a follow-on question to that. How would vulnerabilities in such programs be meaningfully reported?
So most of the vulnerabilities or flow analysis is based on taint propagation, where you have a certain parameter that can be attacker controlled, induced from an untrusted source, traversing through your application and touching a sensitive sink. Again, the vulnerability is specific to the type of source and the sink and few other aspects. On that basis, we begin to connect all of these insights together and conclude that there are symptoms of, as when colluded together, leads for a certain vulnerability to be triggered. So the precision and accuracy is relatively high as compared to any other tools, because as we model and semantically tag information on the graph, we are able to precisely pinpoint what type of weakness or vulnerability can be triggered on that path.
Wonderful, thank you. And thank everyone for all your excellent questions, and the speakers, of course, for your insightful answers. So to wrap things up, we'd like to announce our winners of the $50 Amazon gift cards. Congratulations, go to our 3 winners: Atanas D, Pench B, and Mahima K. So just a reminder that the recording of the webinar and slides will be available via an email link and also on devops.com. And remember to check out the website for more exciting webinars that are coming up. Well, please join me in thanking today's speakers. It was extremely interesting and a lot of great content. We covered a lot of territory. Chetan Kaneki, CTO, co-founder of Shift Left, and Shannon Leitz, director of Red Team at Intuit. Wonderful having you on the podcast. We'd also like to thank our audience, you, for joining us and spending your valuable time on the webinar listening to us. It's been my pleasure to host today's DevOps.com webinar. We wish you all the best and have a great day.